what we were doing. We were quantizing a spin-1 field. And we learned that there were some subtleties because of this gauge invariance. So what we decided to do was quantize in Lorentz gauge. So this is the Lorentz gauge choice. Remember that this isn't a completely great gauge because there's still some leftover residual gauge symmetry. So we're going to have to deal with that as we go along. And what we actually did was not quantize Maxwell theory, but quantize a theory which is equivalent to Maxwell theory only after we impose this condition. Okay? So in the quantum theory, we haven't imposed this condition yet. We're going to go along and do that in this lecture. Remember, we had this mode expansion. The key new thing in the mode expansion was the fact that the mu index on here, I kind of soaked up into a polarization vector. And this polarization vector is a set of four vectors. And they have the following properties, that epsilon 0 is always time-like. Epsilon 3 is always chosen to be longitudinal to the momentum. So it's always chosen to be in the same direction as the momentum. And then epsilon 1 and 2 are transverse to the momentum. Okay? This is just a notational trick, but it's going to have the advantage that when we come to the actual theory, A1 and A2 are going to create physical states. And it's going to be the states created by A0 and A3 that we'll learn how to get rid of. Okay. So what do we do? Well, we found the commutation relations between A and its conjugate momenta. And they came with a rather innocuous-looking delta symbol. But when we translated this into the commutation relations for the creation and annihilation operators, and in particular, we put both indices at the top, this delta symbol turns into a slightly more dubious-looking Minkowski metric. And the problem with this Minkowski metric is that it's indefinite. It's got pluses and minuses. That means that we can never fix this minus sign here so that all of these creation operators give you sensible states. So some of them are going to give sensible states, but the other one, a minus sign, is going to crop up, and that's going to be annoying. So the way we fixed it at the moment, the spatial guys, that's when lambda is 1, 2, and 3, they give sensible commutation relations for A and A dagger. But the A0 one, the time-like guy, that has a minus sign. And the implication of this is that A0, whenever you try to create a photon that's polarized in a time-like direction by this operator here, this has negative norm. Okay. So basically what's happened here is the Minkowski space metric has indefinite signature, and this has embedded itself in the Hilbert space. But having Hilbert spaces that have indefinite signature is not something we know how to make sense of in quantum field theory. So we want to learn how to deal with this. Okay. But by the way, there's a name for states like this that have negative norm in a Hilbert space. People often call them ghosts. Okay, so are there any questions about what we did yesterday before we move on and try to solve this problem? No? Okay, so what are we going to do? What are we going to do is remember that we quantized the theory, but we've still got this constraint. And so it's going to be imposing this constraint together with this residual gauge symmetry, which is left over in Lorentz gauge, that's going to give us a sensible Hilbert space for the theory. Okay? So the question now is that we're in the quantum theory, and we want to know what the right way to impose this constraint is. Okay. So there's a bunch of choices, and I'm going to give you sort of 3 different options that seem to be weaker and weaker ways of imposing this as a constraint. And we'll actually see that they don't make sense until we get to the weakest possible way in which we can impose this. So to remove these negative norm states, we'll try to impose the constraint in the quantum theory. Okay, but how are we going to do this? So here's the first thing that you might think of if you're told to impose this equation in a quantum theory. You might think, well, obviously I'm taking derivatives here with both space and time, so let me turn A into an operator in the Heisenberg picture. Okay, we know how to do that. You can just get rid of the squiggles and put a minus sign there. Okay. So now this is certainly an equation which makes sense if A is an operator in the Heisenberg picture. So you might think, well, I'm not going to consider any operator in my theory. I'm only going to consider operators that obey this constraint. So the first option is that you could try to consider as a restriction on operators in the Heisenberg picture. Okay, it turns out this isn't the right thing to do. This is way too drastic thing to do to limit the kind of operators that you can consider, and it basically just screws up everything. In particular, one thing it screws up is these commutation relations here. Because, okay, I can turn them into equal time commutation relations in the Heisenberg picture, and then I can act with d mu a mu, and I get 0, but I shouldn't be getting 0 here. I should be getting derivatives acting on delta functions. So this restriction isn't consistent with the basic starting point of the whole theory, which is the commutation relations. So this isn't something we want to be doing. This is too strong, and in particular, it's not consistent with the commutation relations. Again, this kind of thing will come up over and over again in different theories. You'll have constraints in some classical theory. You'll want to impose them on the quantum theory, and you need to know what to do. And this is not what you do in any case. You never just impose them as constraints on the operators that you consider. Okay. So our second choice is a little bit weaker. And is actually fairly well motivated. The problem that we're finding in this theory is that the Hilbert space is sort of not as well behaved as we would like. It has negative norm states. So it seems sensible to try and impose this as a constraint on the Hilbert space that defines what the sensible states are. So option 2 is that we could try to define sensible states, where sensible really means the physical states. So we had an operator condition, but we could insist that maybe the only states that we want to consider to be physical are those that are annihilated by this particular operator. And then it might be, if we're lucky, that this is a sensible condition that gets rid of all these horrible negative norm states. Something we could hope for. It turns out that this also isn't the right thing to do because it's too strong. Are there any questions about this? People seem sleepy, confused.
How much area? more.
Yeah, you know, it is a little ad hoc. And to be fair, it took people 15 years. It's not.
With this guy option.
Well, you know, we'll see what the final solution is. I'll tell you when it doesn't work. It's not an obvious description. It's the correct description. And the reason it's correct is because nothing else happens.
Yeah.
So, Chris, you have a question?
You want to, of course.
So let me tell you why this isn't a sensible thing to do, even though it might seem sensible. So, this doesn't work. And to see this, well, it's going to just save me a lot of writing if I just define this, where A plus is the first guy and A minus is the second. This is the guy that contains the annihilation operator. And this is the guy that contains the creation operator. So why is this too strong? Well, let's look at this on the back. We can impose this constraint on the vacuum. Well, the first guy kills it immediately. But the second guy with the creation operator, that doesn't. So this isn't a good condition because it's just way too strong. If you insist that the only physical states are those that are annihilated by this this constraint operator equation, you find that even the vacuum isn't a good physical state. Because yes, this guy annihilates it, but this guy with actual creation operators doesn't give zero when you activate it. So if we started throwing out states that we wanted to be unphysical using this condition, we'd be throwing out even the vacuum, and we just wouldn't be left with anything that was sensible. Yeah.
Is psi any state in the Hilbert space?
Yeah, so this is a condition that says we've got all the states in the Hilbert space. There's some good ones, there's some bad ones, the ones with negative norm. And we want to somehow get rid of the ones with negative norm. Now, what we have is this gauge fixing condition, d mu a mu is 0. So you might hope that if you impose that in a suitable way on the Hilbert space, it would get rid of those bad ones. So this is my first guess as to how to do that. And it turns out that, well, so psi here would be the definition of the good states we want to keep. And so you would hope that we can come up with a condition in which psi is defined in some way as a good state, and that coincides with what we want to be good states, meaning positive good states.
What I mean is that if d mu a mu is very well defined on the Hilbert space, and if we are still in the Hilbert space, then I don't see the difference between this option and the option for the one that d mu a mu is 0.
Oh, so yeah. What's the difference? I guess the first requirement is the insistence that you only consider certain operators in your theory that are allowed. This condition is that you can have any operators, but the only states within your large Hilbert space which you want to consider are those which are annihilated by this given answer.
But then psi is not just any operator, psi is not just any state, it's just a class of states that we want to consider.
Yeah, and it's going to turn out that you will typically need to consider all states, but the only ones that you'll allow physically to be particles you can have sitting in your hand. They're photons, so it's hard to get them to sit in your hand, but you know what I mean. The physical state is going to be the ones that obey something like this.
Can we really consider the ground state as a good state, provided from the fact that we had a lot of problems dealing with the ground state minus that we just have to take the difference? So why should we consider it?
Yeah, it's a good question. So you might think that, well, perhaps what this is telling us is that we have to consider a different ground state. And I guess it was these avenues that people explored for 50 years until they worked out the right thing to do this. So what I'm going to do is not spend a long time telling you what's wrong, but just tell you what the right thing to do is. But just highlight this to explain that people worked on these ideas and they don't work. You can't make them work. So option 3, which is the one that actually does work, is the following requirement. We'll define the physical states within our Hilbert space to be those that obey it should be a psi. To be those that obey the Lorentz condition, but not the full Lorentz condition acting, but just this positive frequency part, so just the part with the annihilation operators. Okay, so the Lorentz condition had 2 pieces. It was this piece with the A minus, which meant the vacuum didn't survive the option 2 condition. So now we just impose this first bit. Okay, this looks really ad hoc now, right? The reason this is sensible is because of the following. So this ensures that for any 2 physical states, that any 2 physical states have vanishing matrix element with the operator. Okay, so this has a name. This is known as the Gupta-Bloiler condition. Okay, so this is the thing that finally is going to work and allow us to have a sensible theory. And I agree, it probably seems like it's ad hoc, but we did have a theory where we had to impose a constraint in the quantum theory in some way. And we've never really come across these situations before, so it's not quite clear what the right thing to do is. And so what I tried to sketch on the board is, if you sat down and thought about it for a day, 3 options you might come up with. Impose the constraint as an operator condition, impose the operator condition on states, or finally, which is clearly weaker, impose that the particular operator, which is the constraint, has vanishing matrix elements on what we want to call physical states. Okay? It turns out that it's this weaker condition that's the right thing to do. Okay? The weakest thing you could possibly do is the right thing to do to get a sensible theory.
That's the whole entire field, right? That A mu.
that you wrote down there.
That's the whole field. The reason is that A plus goes this way, but A minus will go that way.
So they are transposed of each other, A plus and A minus.
Let's see.
Or does that not, as long as we kind of have them?
Not quite.
Not quite. Yeah, well, that's. But it's still enough to act.
But for the operator, it's they're the dagger of each other.
Right. Yeah.
That's all. That's all. Okay. It's also worth pointing out that from this condition, it's not clear that what I call the physical states span a Hilbert space. But from this condition, it should be, because this condition is linear. So in particular, if I have one physical state and another physical state that obey this condition, I add them together, I get a third physical state. That's what I would want from, a good subspace. Yeah.
Why the notation of the plus on the one and the minus on the other?
Yeah, that's due to Heisenberg and Pauli in their paper in 1920. It feels like it should be the other way around. The reason is that if you have, with our signature, this is minus I energy time. And e to the minus I energy time is what we call positive frequency. So that's why this one has a plus. This one has a minus. Okay, so I think questions about this. What I'm now going to do is show you that this condition here, together with something extra, is going to be sufficient to define a sensible Hilbert space and get rid of these negative norm states. Okay? Yeah, yeah. You see that we've got one negative norm state, but 2 extra degrees of freedom. So we're ultimately going to want to kill both the time-like and the longitudinal modes, and we'll see how that works. Okay, so let's try and understand what this physical Hilbert space looks like that's a subspace of the full Hilbert space. So what does H-phys, which is the physical Hilbert space, look like? Which is just a way of saying which states within the Fock space satisfy this condition. Okay, so we're going to decompose an arbitrary state into, so this is really just notational convenience. A general state consists of some number of these guys and some number of these guys and some number of these guys. So what I'm going to do is just rewrite that state in terms of a direct product where the first part, the psi t, tells me how many of the transverse photons there are. And the other part, the phi, tells me how many of the time-like and longitudinal components there are. Okay? Anticipating the fact that I want to keep these guys, but ultimately I'm going to want to do something about these guys. So this contains transverse photons. And this contains time-like and longitudinal. Okay, now what I'm going to do is ask what this condition looks like on a given state. And the key point is that, you see, what's this going to do? It's going to pull down a factor of time, and it's also going to pull down basically a factor of spatial momentum. Okay? It's going to act, we're going to differentiate this expression with respect to time, which is going to pull down a factor of energy, and with respect to spatial momentum, okay, for a fixed momentum p. But because I've done this trick here, where the A1 and the A2 components, they're always transverse to p. They're not going to appear in this expression, okay, by definition, because I'm going to get a p dotted with A and the p dotted with the epsilon 1 and epsilon 2 are 0. So it's really just these two that are going to appear in this constraint equation. So d mu A mu dagger acting on psi is 0 in terms of this mode operator, it doesn't affect what's in here. What's in here is just creation operators from A1 and A2. But it does affect what possible states I can write down here. This is where the A0 and the A3 components are. Okay. So plugging this mode operation into here and using these equations, we find we get the following restriction on what phis we consider to be physical.
For the time-like and longitudinal.
No, so somehow I defined the polarization vectors in such a way so that they drop out, because it's also true that these are normalized. These are also normalized. So they're basically. So for example, if P is, we had this example before. If P is 1, 0, 0, 1, then epsilon 0 is 1, 0, 0, 0, and epsilon 3 is this. So there's just factors of 1. Is that the question?
Yeah, that's good.
And the epsilon 1 and the epsilon 2 don't give any contribution because of this. Other questions? Okay, so we've got these physical states, and it's not quite what we wanted. We didn't just get rid of time-like and longitudinal polarized photons. We can have as many transverse photons as we like. This can be anything with transverse photons in, transversely polarized photons. But this state phi, which contains time-like and longitudinal guys, this has to obey the following, which roughly says that if you've got, so if you don't have, well, let's think about this. This guy annihilates this on its own if this state contains no time-like photon of momentum p. Okay? And this state did the same if this operator does the same if this contains no longitudinal photon of momentum p. So if this guy has no longitudinal photon of momentum p, it also can't have any time-like photon of momentum p. That's what this says. But it also says that if this guy does have time-like photon of momentum p, it better also have a longitudinal-like photon of momentum p, so this term can cancel this term once they annihilate. Okay? So what it's telling us is not that the physical states can't have any time-like or longitudinal photons, but they've got to have equal number of time-like and longitudinal photons. That doesn't sound right. That's what we're getting from this condition. Okay. So it is true. So this condition does eliminate the negative norm states. But it does something that's almost as bad. It replaces them with zero norm states, because the norms of all of these guys necessarily vanish. Okay, you see why these are zero norm states? It's because they contain as many time-like photons as they do longitudinal photons. That's what this expression is saying. So when you take the overlap, the longitudinal photons give you, some number to do with how many longitudinal ones there are, but then you get minus that from the time-like guys. They just cancel. I could do this in some more detail if you like, but believe it's wrong?
You will have one minus sign coming from the AP0, and you will have also a minus sign coming from the...
No, so this condition is you can basically think of as the same. Here's a state phi that satisfies this. AP0 dagger, AP3 dagger. Is that right? No, that's not right. Sorry. Satisfies this.
You want a linear
Actually,
combination of the...
If you compute the norm, you'll have phi AP3 dagger, AP3 phi. You'll have some mixed terms with AP3 dagger and AP0, and you'll have also the same term with AP0 dagger, AP0. Then you have a sign coming from the commutation relations.
Ah, that could be right.
I think
This should imply this, but at the moment, but this is not the right argument. So the right question is,
The question is whether any states not to states that satisfy that fraction. Just start here. Any non-vacuum states.
Oh yeah.
That's the question. I think that's true. Then you have no dimensions.
I didn't think about this hard enough before I stood up.
So if you have like a linear combination of two states, one with then the zero norm, because each state has the longitudinal state has a positive norm and the time accident has a negative norm, and that they cancel each other.
Thanks.
These are one particle states,
So
right?
if I have this, well, I'm going to multiply around that.
Right.
Yeah, thank you. Good. So this is a state which obeys this condition. And if you figure out the overlap of this state, these have zero overlap with each other. This guy has norm minus 1, and this guy has norm plus 1. So the total thing has norm 0. Yeah. Thanks. Good. Let me write that down. I equals AP0 dagger 0 plus A3 dagger P. Yeah, so there's an example of such a state. Okay, so what are we left with? We had this awful Hilbert space that had negative norm states. We managed to impose the constraint from gauge fixing in a sensible way, but we've got rid of the negative norm states and left ourselves with an infinite number of zero norm states. Okay, so we have a bunch of sensible ones that we'd like to keep, and a bunch of zero norm states that it's not quite clear what to do with. So here comes the second part of the argument. And remember, when we quantize in Lorentz gauge, we don't just have the Lorentz gauge condition, but there's also some residual symmetry, some residual gauge symmetry. That wasn't true in Coulomb gauge. That's when we fixed that. But in Lorentz gauge, we had some residual gauge symmetry. The existence of these zero norm states in the Hilbert space is basically the effect of that residual gauge symmetry. Okay. And again, this is a general phenomenon. Lots of theories have zero norm states in their Hilbert space. It's always telling you that there's some gauge symmetry in the theory which is responsible for it. Okay. And what we're going to do, or the correct way to interpret this, is that the gauge symmetry that lived in the full theory, at least this residual gauge symmetry, has itself descended to the Hilbert space. And that if you have a state psi t with one phi here, that's to be considered as exactly the same physical state as psi t with any other phi here. Okay? So all the class of states that differ by adding different phi's, all of which have zero norm, they're all to be considered the same physical state in the space, in the Hilbert space. Okay. So we treat these zero norm states as gauge equivalent to zero, which means if we have a physical state and we add to it any zero norm state, it's a different state in the Hilbert space, but we view it as the same physical state. T brackets.
This might be a little bit out of the scope of this. Define a BRST cohomology for UG1 gauge theories.
Yeah, and it's more useful for non-abelian theories, but yeah, do it here too. I think you'll learn about this.
Usually people do the BRST for non-abelian gauge theory. Nobody mentions it in the abelian context, so that's why I was wondering.
Okay, so let me just highlight this again. So two states which differ just in their longitudinal and time-like polarization modes. So the ones that we know from reality are unphysical. Are said to be physically equivalent. Okay, so that sounds like it would be a good way to make sense of everything, but you know, I don't generally in a quantum theory get to just go and point to the Hilbert space and say these two states are going to be considered exactly the same, because you know, there could be physical observables that give different answers for those two states. So to actually make this fly, what we have to show is that any physical observable evaluated on two states that we want to consider equivalent gives the same answer. Okay? So it's true, you can prove that in general, that any gauge invariant observable has the same answer evaluated on any states that differ by these time-like and longitudinal modes. And I won't prove it in general, but I'll just show it for the Hamiltonian now, which is the most interesting observable. Yeah?
Is associated with this symmetry, or is this really just an invariance and not a...
At the moment, it's really completely a redundancy. Symmetry is not a good name. And you can see that in the language on the board. It's just that the redundancy of the classical theory is descended to a redundancy within the Hilbert space.
But wouldn't theorem still apply? Because we still have all the Gaussians not changing.
So Nernst's theorem doesn't apply, except there's a caveat, which I'll mention in a bit. So we can check that no physical observable depends on phi. So I won't prove this in general, although you can. I'll just show you that for the Hamiltonian, well, you could probably guess the form of the Hamiltonian. Okay, this minus sign rears its head again. So we have all the space-like polarizations contribute positively, but the time-like polarization contributes negatively. But now you can see what happens. So you know, our condition that came from the Lorentz gauge tells us that for as many of these that we have contributing negatively, there's an equal number of the A3s that are contributing positively, and they just don't contribute. So this condition here guarantees that this is true, but this in turn guarantees that the A3 component of this just cancels the A0 component of this. Okay, so the only thing that H actually cares about is the number of transverse photons, transversely polarized photons, and there's no restriction on them. And that's exactly the theory that we want. Okay, so this is how you quantize gauge theories in a covariant fashion. You forget about the gauge fixing constraint. You quantize as if it's not there. You get something that seems nonsensical. You impose this constraint as a constraint sandwiched between two physical states. And then you follow up by getting rid of the zero norm states by insisting that they're a gauge redundancy.
So if we use the Coulomb gauge, we can still just sandwich that Coulomb gauge condition in between.
No, so the Coulomb gauge goes very, very different. I won't have to do it. But conceptually, it's much easier.
Yes.
You get a Hilbert space that's just fine from the start.
Yeah.
It only contains transverse photons from the start. So the physical content is right there in the Hilbert space you define. What's really messy are the equations you get out for, say, the Feynman propagate, which I'll just write down now for this thing. And then you have to work very hard to show that those messy equations are equivalent to the simple equations of the document.
But that prescription you need a recipe for quantizing a gauge. It sort of works.
It's actually a slightly different strategy that you take. So in these gauge theories, you have some constraints that you want to impose. And the path we've taken here, which is typically what's called covariant quantization, basically an autosymmetry, is that you quantize the theory, and then you try to impose the constraints on top of that. In other gauges, like Coulomb gauge, there's something called physical gauges, because they're the ones where the physical degrees of freedom are manifest immediately. What you basically do is you take the classical theory, and you solve that constraint within the classical theory to consider only the degrees of freedom in the classical theory which solve that constraint. And then you quantize those degrees of freedom. Okay? So it's a question of whether you impose the constraint at the classical level first and then quantize, or you quantize first and then you impose the constraint. And of course, everything should agree, and it does.
But then, so if you're doing covariant quantization, can you just sandwich your condition in between two physical states?
Yeah. Right. So that Gauss-Euler condition is something
Okay.
that you use.
So again, other theories that engagement. Okay.
So a great example is string theory. That's also a gauge theory. You'll come across it. And again, there's sort of two standard ways that you can quantize the theory. One is which is called light quantization. And it is very similar to Coulomb gauge. You solve the classical constraints in the classical theory first and then quantize. And it's kind of ugly, but it's easy. Right? And the other one is called covariant quantization. There you do this Gauss-Euler type trick. And it's conceptually much more challenging. But the answers you get are very, very clear. There's actually a third way to quantize, which is the thing everybody does in the end, which is using amplitudes. And so you'll learn how to do it. Questions?
The thing you said about having to work really hard if you do the Coulomb gauge quantization to get the propagate to look like whatever we're going to show. Does this have to do with the warhead entities? Because I know we haven't mentioned it.
Maybe. I'm not 100% sure. Actually, yes, I think it's exactly that. What you get in Coulomb gauge is this horrendous propagator that doesn't look Lorentz invariant. And what you have to argue is that in diagrams where what's coming in are physical states, meaning that they contain just transverse modes, that propagator that's ugly in a very ugly equation you can replace by something nice because of the differences. And the way to prove that is through Lorentz. Although in the notes I go through Coulomb gauge in some detail, and I just kind of walk you through a few simple examples where you can see that actually it's true that you can replace this propagator. So I don't do it. Give a few examples and convince you that it's trouble. Let me tell you what the propagator is, and you know that when we do Feynman rules, what we really need from these three theories are the propagator, because that's what we put in the internal and external lines of diagrams. So the Feynman propagator well, it's dead easy. You plug this into here, you do the same kind of time ordering contour integrals that we had before, and you get the following expression.
Should those be evaluated at the same point?
No, thanks. Okay, so it's exactly the same kind of expression that we had before. In fact, for the spatial parts, a mu, where mu is 1, 2, 3, it's exactly the same propagator as we had for a scalar field. And for the time-like part, there's an extra minus sign because there's a Minkowski vector. Okay? So the propagator is dead easy. Yeah. Yeah, that's the Green's function of that theory it's equivalent to Maxwell theory in the Lorentz gauge. You know, I changed my Lagrange. Yeah, for that Maxwell Lagrangian, it's going to be hard because that Lagrangian wasn't invertible. Remember the actual Max. So then then you run into those problems, which is really why the Coulomb gauge propagator is as ugly as hell. Okay, so we're basically done quantizing the spin 1 field. We've got what we wanted. We've got the propagator, and we've understood that there are all these subtleties in the Hilbert space that are real subtleties that arise over and over again in other theories. So the goal now is to throw in some fermions, tell you how light couples to matter, write down the Lagrangian for QED, and then show you some scattering amplitudes. So are there any questions? No? Okay, so coupling to fermions. We do coupling to matter in general. Good. So we want an interacting Lagrangian. So we start with Maxwell theory. And you know from electrodynamics what kind of interaction we want. If we put something like this here, where this J mu depends on other fields, then the equations of motion are d mu f mu nu equals J mu. Okay? But this is exactly Maxwell's equations in the presence of sources. This J nu is usually called a current in that case. Okay? If you're not familiar with this, then this is an ansatz for the interactions, and this is what we get. However, it turns out we can't put any function of fields here, of other fields J mu, because there's a consistency condition. And the consistency is that just by symmetry, if I act with another derivative, this is symmetric, this is anti-symmetric, so it's 0. Which means that this guy here, this current, has to obey d nu, j nu, when the equations of motion are obeyed at 0. Okay? But this is something we've seen. This is the definition of what we call a current that comes from Noether's theorem. Okay? So if you want to couple a gauge field in this way to some matter, then what you need to do is couple it to a current that comes from, well, that's conserved. But we've got lots of those, you know. We spend days just figuring out what the conserved currents are in different theories. Okay. So now coupling to fermions. So the Dirac-Lagrangian So this is the Dirac-Lagrangian, and we know that this has this nice symmetry, which is basically rotating the phase of psi as a complex field. And this gave rise to a current which was equal to the following. And this tells us that we can write down a theory of light interacting with fermions by coupling this current to the gauge field. So we can consider the full Lagrangian that consists of a Maxwell term plus a Dirac term together with a term which multiplies this current by the gauge field, and this E is a coupling constant. It's some number. Okay. So notice that there's something extremely important here. That we learned that symmetries were important because they gave rise to conserved currents. But now we learn that symmetries are even more important because if you want to couple matter to gauge fields, that's what you've got to do. You've got to find symmetries which give you a current which couple in this way. Yeah. No, at the moment this is a classical Lagrangian, so this can go anywhere. Yeah. Other questions?
How do we know the right place to put it?
Oh, it doesn't matter. You know, you can put it there or there. It's the same.
Well, but I mean, when we go to one.
Oh,
But then it's all dictated by, not even the quantum theory, this commutes with this, because fields of different type commute. So it's the conservation of the current that has to couple to F mu, that could also have been derived using the gauge invariance of the Maxwell.
Good. I'm going to do that now, actually. So we spent all of the last lecture and a good part of this lecture arguing that in order for this theory here to be sensible, and in particular to have just true transverse polarization states, it has to be the case that this is gauge invariant. And that followed from gauge invariant. But now I've added an extra term here, this A mu. And the A mu shifts on the gauge invariant to A mu plus B mu lambda. So it doesn't look as if this thing is going to be gauge invariant anymore. So we need to figure out how this is going to be gauge invariant. So to see that this Lagrangian is gauge invariant, well, we're first going to just introduce some new notation. So this is standard notation. Okay, you write this partial derivative as a capital curly D instead of a small curly d. Okay? And this guy here, remember the slash just means it's a vector that's contracted with gamma indices. Is defined in the following way. Okay? It's called a covariant derivative. Okay, so when you see things like this, it's just some notation that tells you that there's an extra gauge field hiding in here which is interacting with psi.
So that we no longer slash the partial. Oh, never mind. You're writing that. Oh.
Yeah, I wrote d mu, but if you multiply this by gamma, this would be slash, this would be slash, and the a would also be slashed.
I didn't realize that. Sorry.
So the claim, which is very nice, is that this Lagrangian, which is just the same as the one I wrote down, is actually gauge invariant. And the gauge transformation is the following. The gauge field transforms in the way it did before, but you have to make the spinor field also transform. Okay, so notice that the spinor had a particular symmetry that gave rise to a conserved current that we couple to the gauge field. But now, once it's coupled to the gauge field, in order for the whole thing to be gauge invariant, the spinor also has to transform where the symmetry that we had previously is promoted to a gauge symmetry. So it's now lambda of x and not just a constant here. And the lambda of x has to match this lambda here. Okay? So let me just prove that this Lagrangian is invariant under this transformation. So you can see that this doesn't depend on psi, so this is invariant just because it was invariant before. And this term with the m here, this is also invariant because there's an e to the minus I lambda x here and an e to the plus I lambda x there. And they just cancel. Okay? The thing that's tricky is when the derivative hits this, because now the derivative hits both psi, but it also hits the e to the I lambda, and that causes problems. So it's really just this term, the d slash psi term, we have to worry about. So the proof of this is the following. Look at the covariant derivative and see how that transforms. Okay, so you get three terms. The first term is from psi transforming in this way. The second term is from psi transforming in this equation. And the third term is from a mu transforming in this equation. Yeah. So the key part is that this derivative acts both on psi, but it also acts on lambda. But now when the derivative acts on lambda, it gives this term, and this precisely cancels the bit we got from the gauge field shifting. So this goes, and this goes. Oops. And what we're left with is d mu psi again, with this exponential factor taken outside. Yeah, Aaron.
Just we're coupling the fermion spinors to the gauge fields.
Yeah.
Is there any mechanism for how the fermions will themselves alter the gauge fields? Do you have to couple the gauge fields to the fermions?
You mean does this change or?
Yes, because of the fermions have charge or whatever they're moving.
Yes, so the gauge symmetry never changes the way the gauge field is transformed. It only changes the way the matter is. When you couple the matter to the gauge field.
Okay.
Was that the question?
I'm wondering how the fermions themselves will contribute to the field, gauge field.
So we should think of this just as we did for the, say, the Yukawa theory or the scalar Yukawa theory. You have photons which are like the free theory, and spinors which are like the free theory, and now we've added an interaction term. And that's going to introduce certain vertices in Feynman diagrams.
Okay. All right. Okay. Yep.
Does that answer your? I wasn't quite sure what the question was. Is that?
Yeah, that's great.
It is okay. Okay. Other questions? So this is really nice, right? It's somehow this covariant derivative, and they're an arbitrary function of lambda here, and still pull it outside the derivative.
Because the bit you get by hitting the derivative exactly cancels the contribution from the gauge field. So we see now that psi bar, covariant derivative psi, is invariant for any arbitrary function of lambda. Okay, how am I doing?
Trivial point, namely that you modify the derivative to d minus EA over C to be plus EA over C. You modify the derivative using the boson field, but you have no analogous modification of the derivative using the fermion field. So if you're doing supersymmetry, you've started out, you're doing things asymmetrically, and you're in a little bit of trouble.
That's true, but at the same point, this is almost just like nice notation, right? I agree. The gauge field somehow takes precedence and doesn't get changed as much as the other field. Gauge field wins.
Okay, I could tell you how to couple to scalars. It's a little bit more complicated, but as we're short of time, I'm not going to. It's in the notes. It's a page. Read it this afternoon in the tutorial session. There's one extra subtlety, but it's not. You basically introduce the same covariant derivatives. Well, this is a trick you should just know. Whenever you couple a gauge field, and it comes up to back to your question, Darren, and Leo's point, whenever you introduce a gauge field, and I should stress that there's going to be gauge fields for strong interaction, which will be 3 by 3 matrices, and weak interaction, which will be 2 by 2 matrices. And what you do in each case is exactly the same. You want to couple the gauge field to matter. It's dead easy. You look in your Lagrangian, and there's curly derivatives everywhere. And you cross them out and put capital curly derivatives. Okay? Where capital D's always mean, it's gone, but it means little d's plus I times the gauge field, basically. And that's the way all gauge fields, all forces in nature, couple to matter. Okay? You've also seen this before. It's also the way gravity couples to matter, because you've seen these kind of covariant derivatives in general relativity, where it's little derivatives plus the Levi-Civita connection. The Levi-Civita connection is really on exactly the same footing as this A here. In fact, mathematicians call this a connection, but physicists call it a gauge field.
Covariant derivatives coupling, right?
Yeah, that's right.
So I wonder, is there a more complicated coupling that is non-minimal that people just don't use?
Yeah, you can consider couplings following form. It's non-minimal coupling of a gauge field to a fermion. What's wrong with it? When you count the dimensions, this has dimension 4 and this has dimension 3, so this whole thing has dimension 7. So there's some big mass parameter to the power 3 that sits on the bottom here, and this is a very irrelevant.
So that's always the way that...
Always the way, yeah. So the minimal couplings are the ones that are typically marginal, and you'll learn this language, but marginally relevant. They're marginal in the classical theory, but in the quantum theory they become. Well, sometimes not, but yeah. So this procedure, as we just said, changing normal derivatives to covariant derivatives is called minimal coupling. Other questions? Okay. Let me just finally write down the Lagrangian for QED, and we've just actually seen it. So the Lagrangian for light coupled to matter, which means electrons. The following. Okay? Isn't it simple? There's an m here, which is the mass of the electron. You'll learn in the next course that it's not quite that, but certainly related to that. And there's an e that sits in here, which is the coupling constant. Okay? The e that sits in there is related to the fine structure constant. In the following way. The fine structure constant is 137, and it's given by e squared over 4 pi h bar c. By the way, I should have said this. The e that sits in there, it's this e here, is the charge of the electron. Now, it's not hard to see that. You just have to figure out what the conserved quantity is associated to that symmetry. That's the number of positrons minus the number of electrons. And there's an e that sits in front of it that's just telling you the charge that multiplies. So again, it's in the notes, but sorry, I'm not going to have time. Another page in the notes. So this e is the charge. The whole thing is 1 over 137, this famous number. This means the e that sits in the Lagrangian, it's about 0.3. Okay. The 4 pi comes in. Chris?
How do we couple the particles like protons, or which are, you know, composite in some way, or particles that are fermionic but charged neutral?
So the neutral question is very easy to ask. Neutral means they don't couple to the gauge field.
But I mean, where does the distinction from So we just don't write down an interaction term? Okay, so that means they have to arise from a different kind of field than...
Yeah, so you write down a different field for every particle species that there is. So if we wanted to add muon interactions to this, say you wanted to compute the decay of muon-antimuon pair via a photon into an electron-anti-electron, you would add an extra field here, an extra scalar field, an extra spinor field. It would have the same coupling because it has the same charge, it would have a different mass. So there's an extra field for every coupling. The answer to your first question about the proton is a little more involved. So we know protons are made of quarks.
Yeah.
And the way quarks couple to the photon isn't exactly this way. You add fields for quarks, and you add covariant derivative, and now what sits in here is 2/3 of minus 2/3 of minus 1/3 of this. Or, yeah. Alternatively, you might want to work with a description where you don't really care that the protons are made up of electrons. You want to work on an energy scale where we're just not seeing so, where you don't care that the protons are made up of quarks. You might want to work on an energy scale where you're just interested in the protons.
Yeah.
Then you introduce a field for protons. And you couple it as so exactly what you want to do, exactly what you write down depends on what you're interested in, but in your fundamental theory, there's fields for quarks, fields for muons, tau's, electrons, and they all couple to each other. Other questions?
So the interaction Hamiltonian is actually quite big, right? Otherwise, in each one of those terms, never mind answering the question. But you can have mixed interactions, like you can have two muons going in, interacting by or annihilating into photon.
Absolutely, but that happens through two different interactions.
Yeah, and that's the squared term where things start to mix.
Yeah.
Yeah, and you wouldn't have like an electron decaying into muons or anything strange like that necessarily.
No, because the kinematics doesn't work out.
Right, okay, that example. You wouldn't have taus. Oh, you would have taus decaying into. I don't know, I have to think about this.
So you wouldn't have direct couplings between the fermi. There wouldn't be, say, psi electron, psi muon. They always couple via these. But you know, the interact. If you want to add muons and taus, the Lagrangian doesn't look that bad. You can basically do this. And they have different masses, but they have the same charge. So it's really very elegant. The whole of the standard model sort of has maybe 6 terms of this. Wear it on a t-shirt. There was a question at the back.
So if you start from the theory of the quark interactions, and is there a straightforward way to sort of come across the low energy theory where there's a proton field by taking some kind of limit?
Oh no. It's one of the clay mathematics problems. You solve that doing a million bucks. Roughly speaking. It's one of the big problems in physics. Why do the quarks confine? Why are they stuck inside the proton? Why do we get protons and neutrons and mesons, these pions, but nothing else? And all of these questions are completely open. It's a hard problem. I said at the beginning that there are weakly coupled theories and strongly coupled theories, and we can do all this beautiful Feynman diagram stuff if the coupling constant is small. And for quarks, the coupling constant isn't small. So it's a very long. Other questions? Good, so this is the Lagrangian for QED. And what do? Well, we can write down Feynman rules. They're of exactly the same kind that we've been seeing for the last 3 weeks. Oops. So what do you need to know? You need to know what the vertex is and how interactions are mediated. Well, the vertex, it's hidden in this notation, but it comes from the interaction term with a single gauge field coupling to 2 fermions. So here's a gauge field. We usually write gauge field as wiggly lines. And here's 2 fermions. And the Feynman rule tells you to basically, everywhere you see this in a diagram, you include the following factor. Okay, why is that? It's because that's the thing that's multiplying the interaction vertex, okay, with a gamma mu. We've got the propagators. So the propagator for the fermion we worked out earlier this lecture. Sorry, the propagator for the photon we worked out earlier this lecture takes this beautifully simple form because we worked in Lorentz gauge. Propagator for the fermion is what we saw earlier in the week. Okay, and finally we have this kind of annoying thing where all the different lines, and I want an m squared, thanks. Yeah. Where all the different lines here have to be dressed, at least the external lines, with information that tells you what the spin is of the fermion that's coming into the interaction. And now also what the polarization is of the photon that's coming into the interaction. So for external lines, we add the photons. So we just add some polarization vector that stipulates what the polarization is. And for fermions, we add what we saw before. It's the information about the spin. Okay, so remember we had these spinor, fixed spinor 4 vectors, u and u bar for fermions, and v bar and v for antifermions. Okay, again, if you've done this enough now where it should be possible just to read off the Feynman rules from diagrams, but ultimately they derive from Dyson's formula and Wick's theorem and lots of tedious manipulation. And this is just capturing that tedium. Okay, so to finish, I can just write down some scattering amplitudes for you, some real-world scattering amplitudes about QED. Yeah? Chris? Did you want to ask the question before?
I just had something yet, but I'll pass it from notes later. Sorry.
No, I don't think I can give you my notes. Actually, I'm not taking this with me. Okay, let me just write down for you some amplitudes using these Feynman rules. So firstly, electron scattering. So electrons are universally written as E minus, and positrons are written as E plus. Okay. Okay, so I know you spent all afternoon doing these kind of things, so there's two Feynman diagrams. The second one is the same as the first, except they just you flip the labels on these two legs. And by these diagrams, we mean particular equations. These are the amplitude for this to happen. So these two diagrams added together is equal to I'm not going to write the second one. It's the same with the labels flipped. It's almost exactly the same as what we saw for Yukawa theory. The differences are that the propagator is massless because this is a photon exchanged now, and that there's a gamma mu that sits in here. Okay, so the gamma mu is multiplying the spin vectors, and it's telling you that the interactions between spinning particles are going to be different depending on whether what's mediating them has no spin or has spin 1. And this is the way this is appearing. Okay. A nice exercise with which you may or may not do this afternoon. Remember, for scalar Yukawa theory, we took these amplitudes and we turned them into something physical. We turned them into working out what it means for the force between two particles. And we found that there was this particular Yukawa force. You should do the same thing for this, and you'll find that you rederive what we all learned in high school, which was Coulomb's force between two particles. Okay, so it's a nice calculation. We take something very abstract from QED, and we really get something that we're very familiar with. Oh yeah, that's bad. Yeah. Oh, here there probably are. Yeah, this is a P prime. Sorry, thanks. And this must be a Q prime as well. Yeah. Okay, I could. I could write down a bunch more amplitudes and tell you some things about them, but you know, I think I'm just going to leave it here. For the tutorial session today, you're going to be trying to write down a lot yourself. Some of them have interesting properties. If they do, I've written about them in the notes. So I think this is a good point to finish the course. So thanks all for your attention.
So David, I'd like to also thank you for giving this wonderful series of lectures and award you with this T-shirt. It doesn't have any projects written on it, no scattering amplitudes, but it has the key thing, which is the CSI logo. Thank you very much. You're very welcome.
And thanks to all of you. This has been a lot of fun. It's been kind of exhausting, but it's been a lot of fun. And it's been fun because you guys are just fantastic. You're working hard and you're asking smart questions, and you're just really great bunch of people. So I hope you enjoy the next exhausting 10 months.
That's